Not sure I see Raphael. Well, as usual, thank you very much for putting on this really great week of talks. I think now on the last day, it's clear that it's been, very fascinating and a great program. So thank you very much, and indeed, thank you for giving me the chance to talk here. I guess I have to say double thank you. So I was initially giving a short talk, but because Marcus Huber couldn't be here, so Raphael kindly offered me the chance to give a longer talk. So I originally was just planning to talk about this robustness of measurement, which I'll explain. And so now I decided to add on a second work on complexity of compatibility. And hopefully by the end of this talk, you'll understand what I mean by these two expressions. This is some joint work. So both of these projects are with Noah Linden, who's also based at the University of Bristol, who I gather is a bit of a mysterious character because he never travels. So many people have never met Noah. And the second project on compatibility is also with Belen, which we started while she was still in Bristol a few years ago. So as a quick outline, so I'll try and cover two topics. I'm not quite as ambitious as Walter. So first I'll start with this idea of robustness of measurement. I'll tell you about its properties and what it is, and two reasons why I think you might want to care. So kind of two operational significance or operational interpretations of this number which we defined, which I think are both quite interesting. And then I'll carry on talking about measurements, so this is kind of about one measurement, and then I'll start talking about collections of measurements. And in particular, this notion of compatibility as quantified by joint measurability, which we haven't heard too much about this week, actually. So Raphael kind of roughly mentioned it in his talk, but I'll spend a bit more time giving you the definitions. And I'll kind of this led us to this question, which, as far as I know, was not really kind of looked at before, about the kind of how complex sets of measurements are. And we have kind of just some preliminary results about kind of maximally complex measurements, and just kind of very first look at kind of the typical complexity. And then if I have time at the end, I would just like to mention something which I find curious, which is a relation to kind of the closest classical problem about random variables. Okay, so let me start on topic one, something I want to call the robustness of measurement. So I'm going to start by defining it and telling you some of its properties. So the situation I'm going to consider is when I have, say, one single measuring device, which I'm going to call this M, which is just some collection of POVM elements, so positive operators, which sum to the identity, and I have some arbitrary number of outcomes, O. I didn't say this will be in some fixed dimension D, of course, and I have the Born rule, right, which tells me the probability to get the outcome A, given that I performed this measurement on some quantum state. And the question we were kind of interested in, Noah and I, is kind of very vaguely of how informative is a measurement M, by whatever that means, right? So we use measurements to learn about properties of quantum states, and so we were interested to know how, as I said, kind of how informative is a measurement M. And in many cases, it's kind of easier not to define what you mean by being informative, but the opposite. So the kind of an easy place to start is to think, well, what would it mean to be completely uninformative, right? Much like we can kind of easily define separable states in entanglement theory. So I'm going to kind of start backwards, and so I can kind of easily convince myself what I mean by a completely uninformative measurement, the stupid measurement, which would be some measurement C, for kind of classical if you want, where each of the POVM elements is just proportional to the identity, right? So, and if I want these to be positive and sum to the identity, what I'll see is that there's some probability vector Q which multiplies these, right? So this is not anything too deep, but clearly this is kind of completely uninformative because, if I give you any quantum state, then no matter what state I measure, I get these probabilities QA, right? So actually you don't do the measurement, you just output a random variable with a probability distribution QA. So then what was our kind of starting point was to say, well, as in many other kind of kind of resource theories, but I wouldn't really call this a resource theory approach, you could ask this question of how far is a measurement from being completely uninformative, right? So the way that we kind of say, well, states which are highly entangled are ones which are somehow very far from being separable, or states which have lots of coherence are ones which are very far from being incoherent. So this is our kind of starting point, is to let's think about this as a kind of distance measure, and let's think about what this tells us about measurements. And of course, there's many different measures you could consider. And so Noah and I just focused on one particular measure, one that we like a lot, which I'm going to call the robustness of measurement. And what is the idea? It's the same with any kind of robustness-based measure. So you want to think about a kind of a minimal amount of noise, whatever that means by noise. I'll come back to this in 1 second. That needs to be kind of added to my measurement to make it the completely trivial measurement, right? So what do I have in mind? So I have the measurement device M, and I want to kind of degrade it to the point where this measurement device becomes completely stupid. And I'm going to allow myself, by noise, I'm going to somehow think about mixing in another measurement, which is going to kind of destroy the properties of this measurement. And it's going to be somehow related to the generalized robustness of entanglement, where you allow yourself to mix in an arbitrary entangled state. So here we're going to allow ourselves to mix in an arbitrary additional measurement. I'm going to call it n. So I'm going to take my measurement n, and I mix it, and I use this slightly funny notation, but I'm going to kind of m plus r times another n over 1 plus r. So I'm using this r over 1 plus r and 1 over 1 plus r as my quantifier. This happens for all the robustness-based measures. It's a kind of some mathematical properties which you inherit if you take this definition. And I would like to mix this in such that I get some completely uninformative measurement, which is of the form some probability times the identity. Right, so this is the number that we would like to define and study as some kind of how informative a measurement is by how much noise I need to add in the worst case to ruin its ability to tell me anything about a quantum state. So the first thing we should do is just check some of the properties of this, make sure that nothing goes wrong, that it satisfies all the properties we would hope, and indeed it does. So first of all, this kind of one property you would like is so-called faithfulness, by which I mean that this robustness should vanish only if the measurement is completely trivial. And indeed, it's kind of obvious from the definition that this is the case. If my measurement was already trivial, I don't need to add any noise to make it trivial. And if it was non-trivial, there'll always be some amount of noise I need in order to ruin it. So it has this faithfulness property. The second one is convexity. So if I have two measurements now, which I can perform instead of just one, and I could imagine flipping a coin and either perform measurement 1 or measurement 2, well, this shouldn't be a better measurement than either of the measurements individually, right? Like, I'm not doing anything too interesting here. And indeed, this robustness, as is always the case, has this property, so it's convexity. And the third one is probably the one which is the most interesting. And I guess Francesco talked about this a little bit in his talk. So I called it measurement simulation, but you could also call it kind of post-processing. So if I have the ability only to perform one measurement, actually in reality I have the possibility still to perform a kind of set of measurements, because I can classically process the statistics from this measurement, which kind of simulates another measurement, right? So in particular, if I measured M on my system, well, I could get the outcome A, and then I could map it to some new outcome B according to some probability distribution, and this is another measurement which I can essentially perform. But again, you see it's kind of this post-processing. You would hope that this is not a more informative measurement than the one you started with, and indeed this robustness has this property. So again, this is just kind of sanity checking at this stage that we're not doing anything completely stupid. So another reason for checking for the robustness, not about these kind of more operational properties, but from a computational perspective, is that it's possible to rephrase it as a semi-definite program, which have been mentioned a few times again this week. It just means that it's kind of a nice linear type problem, which we can efficiently compute on, in a nice way. And so it's not too important, but if you just play around with this definition I gave in terms of the measurements, then you'll see that you can essentially re-express this robustness in terms of super normalized probabilities, some Q tilde now, and it turns out that, yeah, this robustness is just this sum of these kind of unnormalized or supernormalized probabilities, and I have to subtract 1. And I have this single operator inequality, which says that this number Q tilde times the identity must be larger than the P over M element. So this means that the operator QA times the identity minus MA, as an operator, all of its eigenvalues are positive. So, okay, this kind of shows it's nice linear and you can solve it. But actually, if you look at this and you're familiar, then you'll see that once you've written it in this form, we can get very simply an analytic expression or an exact expression for the robustness. Because what is this constraint telling me? Well, if I want to minimize this QA, which is what my kind of objective here, when am I going to saturate this bound? Well, I'm going to saturate it exactly when QA is equal to the largest eigenvalue of MA, right? So if you just think about this for a little while, you'll see that that's clearly the optimal solution. And so then you get this nice explicit form. So this robustness, which we started off in this kind of geometrical type picture, is nothing other than the sum of the largest eigenvalues of each of your P over M elements and minus 1. Okay. And so given this form, we can now write down very simply a couple of simple bounds. So on the one hand, we know that every P over M element, its largest eigenvalue can never be larger than 1. Otherwise, you won't be able to satisfy the normalization condition. And so if my measurement has O outcomes, because it was just the sum of these largest eigenvalues, I see that I get this bound that it's never larger than O minus 1. Okay. Maybe slightly more interestingly, there's kind of a universal guess, an ansatz to this problem. So if you give me any measurement M, I can define this new measurement N. So I do it in this kind of reflection type way. If this was a qubit, it kind of just reflects in the block sphere. But I take the trace of the element times the identity, I subtract it, and I normalize it. Okay, you can sit down with this. It's easy to see this is a valid measurement. This is a valid probability distribution. And the robustness that I get for this measurement is D minus 1. It's out. So you just plug it back in the formula. It's only 2 lines. And so if I put these two together, what I find is that this robustness, this informativeness of a measurement, is upper bounded by the number of outcomes, by the minimum of the number of outcomes, or the dimension D, because, sorry, D here was the dimension of my Hilbert space. And of course, this can never be larger than D minus 1. So what does this say? Well, it says, of course, if I have a measurement which only has a couple of outcomes, it can never be too informative, because the robustness can never be too big. And I can kind of increase the potential to have more information as I increase the number of outcomes. But somehow the Hilbert space dimension is the thing which limits this informativeness, right? So I can't consider measurements with many, many outcomes and hope to get more information. And again, this is somehow intuitive. This is what you would expect. So let's just try and look at some examples just to make sure that, to just see how this works. And in particular, let's try to check that the most informative measurements are the ones that you would guess if you were thinking about this. So first of all, hopefully this was the one that everyone would start with, is if you take the kind of ideal projective measurements, so some collection of orthogonal vectors, which give you this ideal von Neumann measurement. All of these are rank 1 with one eigenvalue 1, all the other eigenvalues vanishing. So of course, this operator norm or the maximum eigenvalue is 1 in all the cases, and I saturate this bound. So great. The maximally robust definitely are at least the projective measurements. And so I have to admit, initially I thought this would be the only case. I thought this should be naturally the only measurements which are most informative. But it turns out this isn't the case. But actually I'm kind of glad this wasn't the case, because the other class of measurement are actually any rank 1 measurement. Right? So if I give you any measurement with some other number of outcomes not equal to D, say more outcomes, but still all of the elements are rank 1, Well, the condition for this to be a valid measurement is that the sum of these alpha A should be equal to D. And so when you, okay, so the maximum eigenvalue of these guys is just is alpha A. And so indeed, you also get that these are maximally robust. And somehow after the fact, this was also good because obviously they're informationally complete measurements, these like ideal measurements that you can do, which tell you everything about a quantum state or of this form. So I'm also happy that these are the most robust. Okay, so one final thing about the properties. So I mentioned that this was an SDP, and one thing in particular that is nice about SDPs, apart from them being efficiently, they can be efficiently solved on the computer, is this idea of duality. So typically you get another way of writing a problem. Whenever you write down one SDP, there's always a second way of expressing interest. And normally this can be insightful, and so in this case, if you take the primal SDP, the one I wrote down before, and you introduce the multipliers, because it was a constrained optimization problem, you end up at this second completely equivalent formulation for the problem. And this one is, again, so the primal one was very simple, and indeed the dual is kind of simple and has a interesting, there's some interesting structure here, because what am I optimizing over? Well, I have actually a collection of quantum states, right? I need positive operators, which are trace 1. So these are naturally quantum states. This is why I call them row A. And it turns out that the robustness is this kind of interesting trace between the measurement and the state minus 1. So this will be useful for me when I come to the next section and I want to talk about this kind of operational interpretation. And just to say, so of course the primal, we solved it directly, right? So I wrote it down, and then immediately I said by inspection you could see what the solution should be, and you would like that to be the case also for this kind of new formulation, and of course it's also true. So I look at this and I say, well, how can I maximize this expression here? Well, okay, you see straight away that if I take a row A, which is just any pure state, which is in the eigenspace of the maximum eigenvalue of MA. So in particular, there could be, say, multiple vectors in this space. Well, if I just take one of them, then the trace of M times rho is, again, just the operator norm. So this is basically a dual formulation of the SDP for the maximum eigenvalue, but just in a slightly different context. Okay, so with all this in place, so we've looked at all these properties, and indeed it's going nicely, but I think at this point you'd be justified in asking, well, why should I care? Should anyone ever calculate this number? So we were kind of just interested to make sure that there was some kind of good reason for thinking that this is about the informativeness of a measurement and why you might actually want to look at this number. And so we found kind of two different cases, and so I'll now just explain the two of them. And so the first one is going to be a kind of a state discrimination type characterization of this number. So what do I have in mind? So I have in mind the standard state discrimination type problem. So I have some source of quantum states, which is basically an ensemble. So with probability P of X, my source spits out the state sigma of X. Right? So there's I'm encoding classical information into quantum states. And what I would like to do is to figure out which state was prepared in any given time. And so normally when you think about state discrimination, you would then think about, say, optimizing over all measurements in order to do the best differentiation of these states. And so here we're going to kind of go a little bit backwards. So now we're going to say, well, imagine that the only resource I have in order to do this task is the fixed measurement M, right? So this one fixed measurement. And so now I would like to know, given that I can only perform this one measurement, I would like to know how well can I do in distinguishing which state was prepared by the source. So my kind of goal, it's a restricted form of state discrimination. And so I mentioned previously that if I have access to this measurement M when I listed these three properties, the third one I mentioned that, of course, if I have M, I can also kind of post-process the measurement, and I get a class of measurements that I can perform. So actually, in this problem, I should think about kind of the optimizing over the post-processings. So that's one thing I should do. But also I have to kind of fix a figure of merit, right? So I'm going to take say the simplest figure of merit, which would be kind of how well do I do on average if I have to produce a guess for which state was made. So this means that I get this following number, which I'm going to count out. So I'm going to maximize over all post-processings of the guessing probability. And so with probability P of X, the state prepared was sigma of X. I now measure this with some measurement, which I'm going to call M prime, which has an outcome G for guess. And I will get this correct exactly when G is equal to X. So I only want to add up those probabilities where my guess for which state was prepared is equal to the state which was actually prepared by the source. So this is my figure of merit. It's the guessing probability using the measurement M for the ensemble E. This is my total probability to guess correctly. And what I'm going to do is I'm going to compare this to the kind of trivial case, to the case where I have an uninformative measurement, or if you like, the case where I don't measure the state at all. So I have some source of quantum particles, and I don't give you the ability to measure them. So what are you going to do? Well, the best thing you can do in this case is just guess the most likely state, right? I mean, if there's one state which appears almost all the time, then your best guess would be to guess that state, and the probability you guess correctly is exactly the probability that state appears. So these are two numbers. I'm calling them kind of the quantum guessing probability given M, and this kind of classical probability of guessing without the ability to perform a measurement. And so now, having defined this, I can give you a kind of an operational significance. So let me consider this ratio now. It's the probability I can guess when I have access to M divided by this probability in the trivial case. And so I want to think about this number. So of course, if I can guess better quantum mechanically than I can classically, then this number should be larger than 1, right? And what I'm going to allow myself to do is to think about optimizing this ratio over all state discrimination problems. So in other words, I'm going to maximize over every ensemble here, right? In the view that let's think about what I could do given the measurement M in the best case. And then what we were able to prove is that this maximization, this ratio of probability of guessing probabilities is nothing but 1 times the robustness. So this somehow gives you the meaning of this number. And in particular, so now whenever the robustness is non-zero, so whenever it's greater than 1, whenever the measurement is informative in some sense, I can find a game where I manage to guess better than kind of completely trivially. Another way to phrase this is just that in any state discrimination problem, this is my optimal ability to do better, right? So I prefer to write it in this form of the maximization, but it of course implies that for any ensemble E, this is an upper bound. So okay, this is just what I've said. This number is really about this advantage, if you want, in state discrimination. And so how do you prove this? Well, it's actually remarkably simple. So if you take the primal SDP, the one I wrote down on the very first slide, you can prove that this 1 plus a robustness is an upper bound, but you don't yet know that it can be achieved. And then this is where this dual SCP comes in. It turns out that the solution to the dual actually shows you that there exists at least one ensemble where this is achieved. And in particular, if you remember, there were these quantum states in the dual, which were the ones that are in the eigenspace of the maximum eigenvalue. It turns out that if you consider this the optimal ensemble for this game is exactly the one where I take these states and I take them uniformly at random. So let me just do the two examples. I had these two maximally robust measurements. So let's just look at these two games in a bit more detail just to get some intuition. So I want to go back to the ideal projective measurements. So in this case, you'll really see that it's kind of, it works, but in the trivial sense. So what were the optimal states? Well, they were actually just equal to the states from the measurement. So this is the ensemble I'm going to consider. So I'm going to consider a state discrimination problem where I give you a set of orthogonal quantum states uniformly at random. So of course, if I don't give you the ability to measure, you just have to guess one of them occurred, and you'll get it right 1 over d. But of course, if I give you the ability to perform this measurement, then you know which state is performed. You just measure them, and you'll get the right state. So I get that p-guess quantum is 1, p-guess classical is 1 over d, and indeed this ratio is d, which is 1, the robustness, 1 plus the robustness. Maybe the slightly less trivial case, but still pretty simple, is the case where now I do this these rank 1 measurements. So I'm going to consider more than d outcomes and a measurement of this form. Well, again, the optimal ensemble is, again, exactly the same. So now I just have this collection of now non-orthogonal states, but nevertheless, they're still rank 1, and I'm going to think about the game where I'm trying to distinguish between these non-orthogonal states. And if you just plug this into the guessing probability, you'll see that you can, the probability you guess correctly is now the dimension over the number of outcomes O. So I can't do it like here with probability 1 in general when O is larger than D, but I still get this D times improvement over guessing at random. And so of course, this means that I get this D times improvement. So I guess the message is that somehow there is a way to quantify how good a measurement M is at discriminating states, and this is somehow completely quantified by this robustness of measurement. Okay, so while we were at some point, we thought we were going to stop here, but then we had a kind of a second simple observation which allowed us to come up with a kind of a second operational significance, which in some sense, I think I like a bit better than the first one. And so the starting point is to say, well, measurements, I think Francesca was also mentioning this, we can think of them, if we want to think about quantum channels, as a particularly simple subclass of quantum channels, the kind of quantum to classical ones. So in other words, I just do the measurement as before, but I just tag on a quantum state which records the measurement outcome, right? So any kind of channel of this form where you just measure and prepare a quantum system is a quantum to classical channel. And so we were kind of discussing, Noah and I, and we're like, well, we know this is true, so is it the case that this robustness has any significance in this scenario too? This was kind of the question we wanted to ask. And we managed to see actually in a kind of nice way that this is the case. And so to see that, I need to introduce a little bit of background, something I guess I'd seen at some point in my life, but I'd forgotten, if I'm honest, something called the accessible information of a channel. So I'm not thinking about quantum classical channels for the minute. Let me think about a completely arbitrary quantum channel, which takes some quantum state and spits out a quantum state. And let me consider the following kind of task. So I, again, have some source of particles, some state sigma x prepared with probability p of x, which is going to go into the channel and be transformed. And now after the quantum state comes out of the channel, I'm going to perform some measurement on this quantum state and prepare classical information G. So I'm kind of doing a quantum encoding of classical information, send it through a quantum channel, and then turn that quantum information back into classical information. So I've got an arbitrary measurement here at the end, some measurement n. I've got an arbitrary ensemble at the beginning. And so the accessible information, what is it of a channel? Well, it says, let me maximize this mutual information, the classical mutual information between this input symbol x and the output symbol g over all ensembles at the beginning and all measurements at the end. And so let me just go quickly, slowly. So what is this? So this is the mutual information, but to evaluate this, I need a probability distribution. I need some probability distribution of x and g. And this is just the kind of obvious one. With p of x, I prepare the state. It goes through the channel and is transformed into lambda of sigma of x. And then I get with probability, trace of ng times the state, I get g. This is my probability of g given x, right? And so these are my probability distributions. This I of xg is the mutual information, which can be written in a number of different forms, but okay, maybe the most familiar one is that it's the difference between the entropy of x, so the entropy of this p of x, the entropy of the source, minus the conditional entropy, the kind of the uncertainty I have in x, given that I've now seen g, right? So this is this number. So this is, if you go to Mark Wilde's book, he has a a section on this quantity, the accessible information of a channel. So one thing to note is that this accessible information, because it's defined using Shannon entropies, it's really kind of an asymptotic quantity, right? And we know it has relevance when I consider many uses of a quantum channel, then this quantity has some kind of significance. But in general, if you only want to use a channel once, we know typically that these kind of Shannon type entropies are not the relevant quantities, and they don't actually tell you a huge amount. And what we know is, say, all of the work out of, starting with Renato Renner's PhD thesis maybe, but we can think about a kind of a single shot regime where I have one use of a channel, and now you might want to therefore define some kind of single shot variant of this entropy, right? An entropy which is valid for a single use of a channel. And one possibility, so again, Francesco was mentioning the kind of min entropies. So tentatively, I might want to define a variant of the accessible information, which I'll call the min accessible information, where I'm going to do the same type of problem as before, exactly the same game, but now my analysis is going to be different. So I'm going to maximize not the mutual information, but something I'm going to call the min mutual information, which is, there's an interesting paper by Renato, I forgot to put the reference. This is a kind of slightly ambiguous quantity of exactly what you might mean by this. There's a paper where they have kind of 4 definitions, but I'm going to take one of them, say the naive one, which is, let me define the min mutual information by this old formula from the previous slide, but I'll just insert the word min everywhere, right? So I'll define a min mutual information to be the difference between the min entropy of the source x minus the conditional min entropy of x given g. And so just as a reminder, so the min entropy of some classical random variable x is just minus the log of the max over x of p of x. So in other words, it's minus the log of the guessing probability of x. And maybe this already shows where I'm going to go. So this is somehow related to the guessing probability in the classical case. And the conditional min entropy, okay, it has a slightly different form. I'm taking the log, and I get to sum over g of the max over x of pxg. So this turns out that these are the quantities. So what I would like to do is to think about this quantity, the min accessible information of a channel, and I would like to see if there's to kind of calculate this thing. And so this was for an arbitrary channel, but now let's go back to the type of channels that I'm interested in, the quantum to classical channels. So in other words, this is just a measurement. And so what we find is that if I take the log of this 1 plus a robustness, it turns out that this is exactly this min accessible information of the channel. So this, in some sense, gives us a second operational interpretation. So I think about this, the channels associated to this measurement, so my channel is now fixed, and I would like to know what is this information theoretic quantity, and I find out it's just log of the robustness. And this is somehow not independent of the previous result because of the following point. So in this optimization problem, I was allowed to optimize over all measurements at the end. So let me just go back. It was an optimization over all ensembles and all final measurements. But the point is that somehow for a classical quantum channel, this is a classical output. There's some privileged basis, and it's very easy to see that the best measurement is to somehow read the result of the measurement. So I measure in the same basis. So this bit of the optimization just kind of goes away. It's completely trivial. And so all I'm left with is some optimization over the input ensembles. And that was exactly the same type of optimization I had when I was thinking about this state discrimination problem. And okay, the only difference is that previously I had the ratio of guessing probabilities, and the log is exactly the thing, which turns this into a difference between 2 mutual information, between min entropies. So it's kind of it's more of an observation, but it gives us this second operational significance. And I should say, so this work was, say, heavily inspired by lots of the work that's been going on recently on this resource theory of coherence or resource theory of asymmetry. And lots of these results, if you're familiar with those, look very similar. And actually, this gives us, say, a new way of reinterpreting some of the results that were achieved in that context. And actually, Marco Piani was another one of the people who was not able to make it here. So I'll have to tell him about this on another occasion. Okay, so that was where I would have finished if I didn't have a long talk. So now I'd like to switch gears to a second work that we've done recently in Bristol. And yeah, I should say that both of these hopefully will be on the archive very soon. I'm currently the bottleneck, and I'm hoping to get both of them into like finished versions as soon as possible. Okay, so now I'd like to some of our other thoughts about measurements, something I want to call complexity of compatibility, which hopefully will make sense by the end of this talk. So first, to talk about this, I need to introduce a bit more carefully this notion of joint measurability of a set of measurements. So I want to consider now a situation, instead of just having one box which performs one measurement, let me consider a collection of, say, m boxes which performs m different measurements, and I'll use this kind of notation inspired by probability theory to say that the POVM element corresponding to measurement 1, I'll delabel them of m of a given 1, etc. So hopefully in a kind of intuitive way. And so what is joint measurability? Well, it's a notion of kind of compatibility for measurements which works for kind of arbitrary POVMs. So which is kind of extends notions which work very well for ideal projective measurements but fail for arbitrary measurements such as commutativity. And so the basic idea is still the same. So I'm going to say that a set of measurements, this collection of measurements mx, I'm going to say that they're compatible if there exists a single parent measurement, so one measurement which I can perform in place of all of these measurements, right? So I can kind of do this one measurement and it tells me exactly the same information that doing all of these measurements individually would tell me. And so in particular, what I want is some measurement, say, g, with outcomes g of lambda, and I need some kind of collection of post-processings, so some probability distributions, p of a of x given lambda. And what I'm going to demand is that I can find this set G and this probability distributions P such that I satisfy this set of kind of equations. So it says that the POVM element corresponding to outcome A of measurement X should just be the sum over all the outcomes where I weight the corresponding POVM element by P of A given X and lambda. So why do I take this as my definition? Well, it means that somehow the probability for any quantum state to get the outcome A given that I made measurement X is just the probability to get the outcome lambda given that I made only the measurement G, and then I post-process, right? So somehow the idea is, a priori I thought I had to choose which measurement to make on my quantum system, and actually in reality I don't have to choose. I can make this one measurement and I learn all the statistics. So this is the notion of joint measurability. And as I said, it's more general than the notion which maybe, if you've never worked on this topic, that you may have thought was the correct one, which is commutativity. And probably the easiest way to see this is with a very simple example. So let me imagine, the simplest case, two Pauli spin measurements on a qubit. So I'm going to take kind of a noisy version of measuring Z and a noisy version of measuring X. So what I'm doing here is, instead of normally eta would be equal to 1 if this were an ideal measurement. So now I introduce this parameter eta, which basically shrinks the block vectors of these measurements, right? And so, oh, sorry, Howard. Well, in the sense, I never perform these measurements anymore. So a priori, I was going to perform either M1 or M2 or MM. And now I just measure G on my quantum state. And then I just post-process this data. So if a collection of measurements has the property that there exists a G, that this equation can be satisfied, then I'll call that set of measurements jointly measurable. And so maybe I said it backwards. So we're interested in those sets of measurements which have this property. So most sets of measurements won't have this property, but some measurements do, which in particular, so the reason why it's more general. So if I consider this kind of pair of measurements, then if I just looked at commutativity, then I'll see that the POVM elements here never commute with the POVM elements here for any eta which is not equal to 0. So somehow you may have naively thought then that these measurements were never compatible and never jointly measurable. But this was not true. It turns out that there is a parent measurement of this form that I want as long as eta is less than 1 over square root of 2. And probably the easiest way to see this is with a picture. So let me consider a kind of a slice through the block sphere. So I'm going to just essentially depict the block vectors of these measurements. So I have the measurement for Z has the 2 outcomes, m of 0 given 1 and m of 1 given 1. So these are not full length because eta is a bit less, is going to be, say, 1 over square root of 2. So I have this first measurement and this second measurement here. And so now it turns out that there's a very nice, simple parent measurement G, has 4 outcomes, which are just in the diagonals. So I can consider a 4 outcome measurement. The length of these vectors is actually a half. And so what I can do is I can say, I take these 2 and I sum them up. And what I find is that this is equal to m of 0 given 1. I take these 2, I sum them up. It's equal to m of 0 given 2. I take these 2, I sum them up. It's equal to m1 given 1, etc. And so what it means actually is I can make this 4 outcome measurement and I just sum the probabilities of these 2 events and it will be exactly the same as if I measured this m of 0 given 1. And I can sum the probability of these 2 events and it will be exactly the same here. So somehow I didn't need to perform these measurements. I just perform this 1 4 outcome measurement and I get the same information. So this is the kind of generalized notion. So why do I think this is, say, the nice notion for compatibility? Well, it turns out that this is particularly relevant when we come to think about non-locality and, say, steering. And the main point is the following. So imagine one party, let's say Alice for the sake of concreteness, performs measurements in some Bell test or in some steering test, which happen to be jointly measurable. Now, it's a kind of a one-line proof that actually then what you'll realize is that you can never demonstrate steering and you can never demonstrate non-locality. So actually the fact that the measurements are jointly measurable imply immediately that those statistics will have a local hidden variable model in the case of non-locality or a local hidden state model in the case of steering. And this is true for any state. So even if I give you entanglement, if you don't use measurements which are non-jointly measurable, then you can't see steering. So in other words, non-joint measurability is the necessary property for non-locality. And yes, I wanted to say, okay. And so actually, so Marco Piani and with Nicolas and Tamash and also the group of Ottfried Gunnar a few years ago, they actually even showed something a bit nicer for the case of steering, which is actually the fact that every set of non-jointly measurable measurements, I can somehow witness the fact that they're non-jointly measurable because they can always lead to steering somehow. So it's really there's a very nice mapping between joint measurability and steering, which somehow says that this is really a nice property of compatibility. So yeah, this is just to say why we might care. Okay, so in order to actually get to this idea that I want to talk about complexity, I'm going to need to introduce a couple of ideas or some kind of terminology which will allow me to say what I want to say a bit more carefully. And so the first thing I want to talk about is something, I didn't know a better name for this, so I'm open to suggestions, but what I want to call a canonical parent. So there's a kind of a subset of parents, a subset of post-processings, which turns out are sufficient to consider to answer this question of joint measurability. So whether or not there exists a parent G is a particularly nice set. And in particular, you can do it in a way which is kind of inspired from Bell non-locality. So I had all of these measurements with all of their outcomes. I can actually consider the kind of the string of all possible outcomes that could have occurred if I performed each of the measurements, right? So some outcome A1, which I want to think about as being associated with M1, some outcome A2, which I want to think about being associated with A2, etc., etc. And now it's a kind of a geometrical type observation, but so if I give you these post-processings, which I talked about a couple of slides ago, the P of A given X and lambda, well, it turns out that any probability distribution of this form, or more carefully, some collection of probability distributions for each X and A, I can always write it as a combination of another probability distributions some probability to get the string A given lambda times by this delta function. So it's where I only sum up the cases where the outcome A for the xth bit of A is equal to, of this bit string is equal to A. So sorry, I'm saying this in a clumsy way. All I'm saying is that kind of probability distributions can be written as convex combinations of extreme points of the set, and these extreme points happen to be deterministic functions. This is what we use in non-locality all the time. And so we restrict ourselves to local deterministic strategies for Bell non-locality. For joint measurability, we have the same possibility open to us. So we can somehow think about kind of deterministic type parents. And in particular, without loss of generality, a set of measurements is jointly measurable if there exists a collection of measurements G labeled now by these strings A, and now this post-processing is just that, well, I take A to be the xth bit of the bit string A. So it turns out this is without loss of generality. And I want to call this kind of parents of this form, where I've replaced lambda by the bit string A as somehow canonical parents, and I don't have to fix the post-processing. The post-processing has become absolutely fixed for me. So why do I care about this? So in some sense, I like to think about this, at least for the space of two outcomes, as some kind of hypercube type representation where I just have a very nice decomposition of this set. But okay, maybe I don't want to elaborate on this. Okay, so now having introduced this idea of canonical parents, let me just quickly talk about some of the implications. So first of all, one reason why we actually do this is because, again, it turns a problem of joint measurability explicitly into an SDP, and so that means we can actually calculate it. So this is nice. So this is kind of on the positive. But then there's kind of a negative side, if you like, which is that this canonical parent, if you think about how many bit strings A I have, well, there's actually, if each of these measurements has O outcomes, and there's O to the M elements. So this means that my measurement has somehow blown up in size, right? I had a collection, a relatively small collection of measurements, each of which had a small number of outcomes, and all of a sudden I'm looking for the existence of a parent which has exponentially many outcomes in the number of measurements. So it actually stops us doing the SDP, because at some point you simply just can't write down, the computer just can't take all of these input bits, so we get kind of restriction in how far we can go in understanding joint measurability because of this fact. So somehow the question we got interested in with Noah, in particular in Bristol, like he was the one who kind of started this project, is he was interested in the question of to what extent is this exponential complexity really necessary? So somehow we think about normally that the interest is in non-jointly measurable measurements, but in here we're particularly interested about the opposite sets which are jointly measurable and therefore kind of compatible, but which somehow we're interested in the structure of this set, and in particular the fact that there's this apparent exponential complexity. So this is what I want to talk about in the remaining time. So first of all, I'll just be careful. So of course it's not necessarily the case, once I try and write down this measurement G, that all of these POVM elements are non-zero. Right? And then if this is true, it means that actually I never need this outcome for any given state. So in particular, what I should really define is that I should be a bit more careful in defining this number of outcomes. I should just count the size of the set of the subset of all strings such that this G of A is not equal to 0. So this is really the number I care about. And in particular, it's kind of, so having thought about this, then you can go backwards and you can realize, well, actually it's very easy to cook up examples where the parent is actually extremely small, right? So one example would be, okay, again, my parent is in orange, so I take a 3 outcome POVM, and because I have 3 outcomes, I can kind of coarse grain in 3 nice ways. So I could think about this pair of outcomes relative to this one, so this defines one measurement, this pair of outcomes relative to this one, it defines another measurement. So here I can cook up a collection of 3 measurements, which I know has a parent with only 3 outcomes. But somehow when I started, it looked like I might have needed 8, but only 3 of the 8 are non-zero. So indeed, it's kind of clear that parents can be very, very simple. But somehow so a second observation is that moreover, in general, this canonical parent that you might write down for some set of measurements, imagine you find a canonical parent. Well, actually, in general, it's not even unique, right? So in particular, imagine you found some parent G. Now I can, relative to this parent G, I can kind of define a set of operators O, which have this nice property that, so they're gonna satisfy this set of conditions for each A and X, that they should be 0, and I want them to satisfy this operator inequality. So if I can find such a set of operators O, then it turns out that G prime, where I take now the measurement G plus O, is also a parent. This is kind of, these conditions are exactly the ones I need in order that G prime is a parent. So using this, I can use this trick to say eliminate some of the measurement outcomes. And again, the reason why this is important is because when you come to solve the SDP, typically it finds solutions with many, many outcomes non-zero, so it doesn't guarantee to you anything that there's a simpler parent, right? There could be a parent with many fewer outcomes, but the SDP has just found one with lots of entropy. This is typically what they like to do. And so you don't learn too much about the complexity of the measurement. Okay, so then let me define, sorry about introducing all this notation, but I'll kind of define the class of parents for a set of measurements M. So this will just be all the parents which are able to reduce the set of measurements M. Okay, so then finally this allows me to get to where I want to go, which is to say, well, our idea was to say, well, the size of the simplest parent, so I give you a set of measurements and now I try to find the simplest parent, by which I mean the parent with the smallest number of outcomes, is somehow a measure of the complexity of this set of measurements. If I need lots of outcomes, then this set of measurements are somehow much more complicated than if I can get away with only 3 outcomes, like in this simple example that I gave you. So we'll define somehow a complexity of the measurement. I'm going to minimize over all parents and trying to find the parent which is simplest in the sense of minimal number of outcomes. And the kind of questions that this led us to are the following. So we realized we didn't know much about this number at all. So for example, we don't even know if there are sets of measurements which are maximally complex. So do there exist sets of measurements where I need this exponential number of outcomes? The SDP finds them, but maybe I could always find a simpler one. Maybe there was always a case that this O to the M is somehow not really real, but just a convenient number in order, framework in order to always find something simpler. Also, again, you might be interested in the typical behavior. Maybe there are very complicated ones, but maybe most sets of compatible measurements under some kind of natural measure on the set of compatible measurements is kind of simple. And also, okay, we don't know anything about this, but you might wonder if there's some additional structure or interesting properties that measurements which are very complex have compared to ones which are very simple. So these were the kind of questions we were motivated by. We don't have a huge number of answers yet, but we're kind of looking at this, but I still thought it was a good idea just to kind of advertise what we know so far. Okay, so the first thing we tried to do is to say, let's, as always, start with the simplest case. Let's look for maximally complex sets of measurements, and let's consider sets of 2 measurements with 2 outcomes in qubits, so it doesn't get any simpler than this. And we can actually go back to this example I gave before. So I gave you these 2 noisy spin measurements, and I kind of told you, well, there is a parent with only 4 outcomes. So now the question is, well, could I cross one of these off? Could I get rid of, say, G naught naught and find another parent which now only had 3 outcomes instead of 4? Okay, as I said, these measurements are compatible for less than 1 over 2. And what you can show, it's actually kind of nice, is that if you assume that one of these elements is 0, then I actually get 4 equations in 4 unknowns, and actually I can solve explicitly. And what I find is that these are kind of potential parents, because I just look at the equality constraints, I don't look at the positivity constraints. And what you'll see is that if you make this solution, you'll find that the only parent which is potentially possible always has a negative eigenvalue and is therefore not a valid parent after all. So in this case, we see in the simplest case at least, but kind of one where I need all 4 outcomes in order to reproduce these measurements. Okay. But now also let's try and build up. So the next simplest case we were actually able to find would be 3 measurements now only with 2 outcomes, so on qubits. And what we found is we found this kind of interesting collection of 3 POVMs, which are kind of constructed in a qubit way. So this x01, I mean the sigma x, but on the 01 subspace of this qubit, and x02 is similar in the 02 subspace. So we found this collection of 3 measurements. The numbers are not too important. They just help us with the analytics. And we were able to show analytically that this set is jointly measurable. Okay, the parent, it's not too horrendous. It has a kind of interesting form. And now we were left with this question. So how do we prove that there's no parent with only 7 outcomes, right? So this would be our goal. If it's maximally complex, it means that this parent with 8 outcomes is good, but there's no, again, if I try to cross anything off, then I definitely cannot do it. And so, okay, the kind of tool we realized that we could use is that this modified semi-definite program, where I have for joint measurability now with a fixed outcome set, which is some subset, is actually still an SDP. And in particular, okay, I don't have much time, so the form is not too important. But you write it in a form where you kind of get a certificate, a number, which implies that there's no solution. And again, I talked about this in the first half. SDPs give you this tool of duality, and duality means that actually you get something interesting, which is like a certificate or a witness of when the problem is impossible. So you can use SDP duality in order to prove analytically that there's no parent with 7 outcomes, for example. This is the kind of the task you have in mind. Okay, so the dual SDP, again, the form is not important. I just flash it up. But for these measurements that we have in mind, what we were able to do, and we were just interested to know that in one kind of non-trivial case, we could do something analytic. So we were able to find a kind of an ansatz for this dual SDP, which proved that if you try to set any of the 8 outcomes equal to 0, that it's infeasible. So it's a bit of a mess, but in principle it works, and it could be generalized. And so, yeah, in each case, we got the certificate, and so we managed to show that this set is somehow also maximally complex. So then going beyond this, so we just then ended up trying to do some numerics, and we considered sets of up to 10 measurements with 2 outcomes. Actually, in every case, we managed to find maximally complex measurements. So measurements which require up to 2 to the, so in this case with 10 outcomes, I found sets of measurements which need 2 to the 10, the parent have 2 to the 10 outcomes. So indeed, it does seem that this idea that there are now sets of measurements which are very complex and need this structure. So then our conjecture is that this is true more generally, that actually in any dimension D with any number of outcomes O and any number of measurements M, we would like to believe that this is true, but at the minute we have absolutely no idea how to prove it. So again, this is why I'm kind of advertising this in case anyone finds this interesting. Okay, so I think I won't say too much more. So we were also interested in, say, typical complexity. So again, this idea of if I somehow pick a set of compatible measurements at random, whatever that means, what's the chance that it's that the complexity is very high? So this seems kind of, to formalize this felt a little bit difficult, but one thing that we realized how to do is to look at the complexity of kind of extremal measurements. So measurements on the set of compatible measurements, we were able to kind of, we came up with a way of randomly sampling from these with some kind of induced measure from the Haar measure. And let me just flash up the results. So we then did some numerics. So in lots of cases, we found that you get lots and lots and lots of maximally complex measurements. But the only cases that we found that were kind of non-trivial were this case of, like, for qubits now with 2 outcomes and 2 outcomes, 3 measurements. So I showed you for qtrits, we could find one with 8. So actually, even sampling the boundary, we didn't find any with only 8. So this is a bit surprising to us, but we don't know what this means. It could be that my sampling is not big enough. And then, okay, going to, it's qubits again, but we see some kind of interesting statistics on the boundary. So we don't quite know what to make of this, but as I said, this is kind of preliminary. And so I think I will skip this because I really have time. So let me just go straight to the conclusion or the summary. So what have I tried to tell you about today? So I've tried to tell you about 2 results. One about this notion of robustness of measurement, which I think is, I'm fair to say, is an operational quantity, which tells you kind of information about how good a measurement is for state discrimination or as a quantum classical channel. And I've tried to advertise briefly this idea of what is the structure of the set of compatible measurements? How complicated does this description get? Is there any interest in looking at sets of measurements which are very, very complex? So this is something I would like to look at more in the future. And I think there are many questions, especially in this second direction, which I would still like to explore. And I say thank you.